It's my pleasure to introduce the first of this session. Will be Daniël Otten talking about models for axiomatic type theory.
Thank you. So, models for axiomatic type theory. In order to understand that, we should first explain what axiomatic type theory means. So with axiomatic type theory, I mean type theory without any reduction rules. So no beta reductions, no eta reductions. You could call it static in a way. The only equalities that we have are definitional equalities. And we will compare two semantics for a minimal version of this HoTT. So on the one hand, we have comprehension categories, so a more traditional notion that closely follows the syntax and also the intricacies of type theory. And the other notion that we will study is that of path categories. These are a bit more concise and use a lot of intuition from homotopy theory. Both of them are only models in a weak sense because they only specify substitutions up to isomorphism. But we know that for comprehension categories, we can turn them into actual models where we do have substitutions up to equality. So our contributions are as follows. We show that path categories are equivalent to certain comprehension categories. And this allows us to turn these path categories into actual models as well. And in addition, we introduce a more fine-grained notion, that of a display path category. And we also prove a similar equivalence for that. And in the end, we will obtain the following diagram of two categories, where we have these path categories on the left, and then suitable notions for comprehension categories on the right. So to talk about axiomatic type theory, we have to talk about equality. So in intentional type theory, we have two notions, the definitional one and the propositional one. And definitional equality forms a fragment of propositional equality. We can view this as the fragment that the computer is able to check for us. The fragment that's simple enough that we don't need to specify it further. But it's also useful to look at other fragments. So if you have larger fragments, then it makes it easier to work within the system, because we don't have these coherence issues that may come up with propositional equality. While for smaller fragments, it's easier to find models. And the two extremes of this are extensional type theory, where everything is definitional, and axiomatic type theory, where nothing is definitional. And to motivate these other fragments a bit more, so for larger, I think this example is nice, where we define addition on natural numbers using recursion on one of the arguments. And we can then prove that the equalities also hold for recursion on the second argument. But here we only get propositional equalities, not definitional ones. But it is possible to add these as definitional equalities without losing the nice properties such as decidability. And some proof assistants, so for example ACTA, allow you to add these as rewrite rules, making them essentially definitional equalities. And for smaller, one example is cubical type theory, where we have path types instead of identity types. So we only have a propositional version of the beta reduction rule. And another example is co-inductive types. If we add a definitional beta rule, then type checking becomes undecidable. So usually people restrict to a propositional version of this rule. And then questions that come up are complexity and conservativity. So complexity varies widely between these theorems, where extensional type theory becomes undecidable. Intentional type theory is of course decidable, but non-elementary for type checking. And in HoTT, because we do all of the work for the computer has to check almost nothing, and it becomes quadratic. And the other question is, does more definitional equality allow you to prove more? And the answer is yes. Namely, we can prove binder extensionality, which is a version of function extensionality that works a bit better in the axiomatic context. And the other thing is uniqueness of identity proofs. However, these are the only additional things that we can prove. So if you add these two as axioms to axiomatic type theory, then they prove the same statements. So now let's look at a minimal version of this axiomatic type theory. So the only thing we really need is a notion of propositional equality. So let's start by considering the normal rules for the identity type. So we have the normal formation and introduction rules. We have this notion of path induction, where we only have to check things for reflexivity. And then we also have this reduction rule or definitional equality. So if we really want to work in this minimal setting without pi types, then we have to strengthen some of these rules. So for the elimination and the computation rules, we have to add in this additional telescope delta. And then because we want to do axiomatic type theory, we want to get rid of this reduction rule on the bottom, so we changed it into an axiom. So we require that there is a term of this equality type. So now the question is, how do we model this? And I would say there are two options. So first off, we can follow the syntax and rules. And this is what's being done in a comprehension category. So we really require that we have a type and these terms. And the other option is to use our intuition from homotopy theory. And this is being done in the path category, where we do require the formation and the introduction rules. But instead of having these elimination and computation rules, we say that this raffle is an equivalence for some suitable notion of equivalence. And that turns out to be sufficient to recover these elimination and computation rules. And because these two are the most complicated ones, this simplifies the semantics a bit. So first off, let me say a bit more about comprehension categories. I think most of you have seen this definition maybe before, but very quickly, in a comprehension category, we have a category of contexts, a category of types. Also, we have this terminal object in the category of context, which is the empty context. And then for every type, we have a context morphism, the display map. And we view the codomain of this morphism as the context in which the type lives, and the domain as this context extended with the type. And then this morphism is the projection that forgets about this A and only keeps the context. And importantly, we also have this notion of substitution. So if we have a type in context gamma and some context morphism going to gamma, then we can find a substitution for this morphism. And then we also have some additional properties that I won't go into for now. So we have context and types as primitive notions. We can also define what a term is. So we say a term is a section of this display map. And then in the comprehension category, we only model the basic structure of type theory. So if we want to model more, then we need some additional requirements. So for equality types, identity types, we require that we have the following. So type and these terms, where we follow the specification given in the syntax. And we also want a notion of weak stability. So we want that for every substitution sigma, that if we substitute for this, that we also get at least an equality type back. So where we also have these refl, int, and beta constructions. But then to get strict models, we need some additional things. So we need that our notion of substitution works well with all of the structure we have. So we want that it works well with the identity and the composition. And then we also want our notions for equality, for the identity type, to be strongly stable under this substitution. So we want all of the following equalities to hold. And it turns out that we can turn a comprehension category into one that satisfies this. So this is the left adjoint splitting, described in Loomsteen and Warren. And then Raphael Bouquet also expanded on this, specifically also for these propositions, these identity types with a propositional beta rule. And then let's go on to the other notion of semantics, the path categories. So here we use a lot of homotopy theoretical notions. So this is closely connected to Quillen model categories, for instance. So in a path category, we have two classes of maps. We have the vibrations, so things we can lift against. And these should be closed under pullbacks and composition. And we also have these weak equivalences. And these should satisfy the 2 out of 6 rule, which is a bit stronger than the 2 out of 3 rule, saying that if you have 3 composable morphisms, and we know that the composition of both of them are equivalences, then all of the other ones are also equivalences. And then if we have a map that's both a vibration and an equivalence, then we require the following. So we require that isomorphisms are trivial vibrations. We require that these trivial vibrations are closed under pullback as well. So we already know that the pullback of a vibration is a vibration, but we need this axiom to see that it's also a trivial vibration. And then we require that every trivial vibration has a section. So these trivial vibrations will play the role of the contractible type families, and we want them to actually be inhabited. And then lastly, we say that we have a terminal object, and that every morphism to this terminal object is a vibration. So everything is vibrant. And then importantly, to sort of get a notion of identity types, we also require path objects. So we require a path object for every object A, which is a factorization of this diagonal map into a weak equivalence followed by a vibration. And here we view this PA as the space of paths in A, where S and T are the source and the target maps, so the endpoints of a path. And R is the map sending every point to the trivial path, the constant path. And in a path category, we can do some homotopy theory. So this is a setting that's sufficiently strong enough to have some of the basic definitions. So we can define what it means for 2 morphisms to be homotopic, namely when there exists a homotopy, so a map from A to the paths in B, such that if we compose this with the source and the target maps, that we get our original 2 maps back. And then we call a morphism an homotopy equivalence if it has an homotopy inverse, a quasi-inverse. So a map going the other directions, such that the compositions are homotopic to the identity. And in this setting, we can show that the homotopy equivalences are precisely the weak equivalences. So we can just talk about equivalences. There's no need for these adjectives. And in addition, we can prove a lifting theorem. So if you have a commutative square as follows, where we have a vibration on the right and a weak equivalence on the left, then we can find a diagonal map. So we can find a map that goes from B to C, uniquely up to homotopy, such that the lower triangle commutes and the upper triangle commutes up to homotopy. So here we have a slightly weaker notion of lifting than maybe we see in other cases. But the fact that this upper triangle doesn't commute on the nose, but only commutes up the homotopy, corresponds precisely to the fact that we only have our beta reduction rules up to definitional, up to homotopy as well. So this is really essential to get a model for this axiomatic type theory. So now the equivalence. So the first and I think the most interesting direction is going from a path category to a comprehension category. So we can view a path category as a comprehension category by just taking this category as a category of contexts. We take the types to be the vibrations. So the full subcategory of the arrow category given by the vibrations. Then the display map that corresponds to some vibration is that vibration itself. And for substitution, we can take pullbacks. And we can show that it has some additional structure. So we can show that this comprehension category has weakly stable identity types, weakly stable sigma types with these beta and eta reduction rules. So to be clear, we don't have these beta reduction rules for the identity types. And then also contextuality, which intuitively means that every context is finite. We can get it in finitely many steps by starting with the empty context. So first off, weakly stable identity types. The formation and the introduction rules are sort of built in or required by the path category, where the source and the target maps follow the formation rule, and then this constant map morphism is the reflexivity rule. And then our elimination and beta axiom, these follow from the lifting theorem and the fact that this R is an equivalence. So here we really use the homotopy theory that we can develop inside of such a path category. And we also get weak stability because path objects are preserved by taking pullbacks. And this uses ideas present in Van den Berg 2018. Maybe a bit surprisingly is that we also get sigma types because we intended this to be a semantics for type theory with only identity types. And the intuitive reason for that is that in a path category, we do not really distinguish between extending the context with a single type or doing any number of extensions. So the requirements on a comprehension category can be simplified to the following. We want for every context extended with an A and a B, we want to find a single type such that we can do this extension using only that type. So we want an isomorphism between these two contexts, making this square commute. And this holds in path categories simply because vibrations are closed under composition. So we don't even need an isomorphism, we can just take an identity map and we can just compose them to be this new display map. And lastly, we have contextuality. So comprehension category is contextual. If for every context, we can build it in finitely many steps. So if a type in the empty context, a type in the previous context, and so on, in such a way that we can find something isomorphic to the context that we started with. And this holds in path categories because every map to the terminal object is a vibration. So we don't even need finitely many steps, we can do it in one step. And then the other direction, so starting with a comprehension category, obtaining a path category works as follows. So if you have a comprehension category with the right structure, then we can define vibrations as the compositions of display maps and isomorphisms. We can define weak equivalences as the homotopy equivalences, and path objects as the identity types. So this is the easier direction because in the comprehension category we have rules for all four, so introduction, formation, introduction, elimination, and computation. Well, in a path category we only have the first two of those. And that's then this more fine-grained notion of a display path category. This is the idea that we can distinguish having only a single extension or an arbitrary extension. So we want to have some more structure. We want to know which of the vibrations correspond to having a single extension. So instead of vibrations, we can now use display maps as a primitive notion. And then we define the vibrations to be the compositions of display maps and isomorphisms. Where in addition, we can replace these path objects for objects, for contexts, with a seemingly weaker notion, so path objects for display maps. Where the idea is normally in type theory we only have path objects for types, while in a path category we require it for contexts. But this is sufficient, so we can use the lifting theorem, and we can use a notion of transport in order to construct our more general path objects. And then we get the equivalent, so we have the following diagram of two categories. Here the U's are forgetful. F is free, going from a comprehension category to one that has sigma types by replacing the types by the telescopes. So an arbitrary number of extensions. And then the C is co-free. There we go from a path category to a display path category by simply saying every vibration is a display map. So I will end this talk with some open questions. So for these identity types, we could simplify them in the semantics by requiring that one map is equivalence. So the question is, can we do this for other type formers? So in particular for sigma types and pi types. So now that we have a notion of path category where sigma types are not already built in, we can talk about this weaker notion that doesn't have reduction rules. And then the question is, can we state them as homotopical left and right adjoints of the pullback functor in some way? And it would also be nice to connect this a bit more with the work of Maietti and Clarenbeau and Debier. So let me end with a page of references. So thank you.
We have some time for questions.
Yeah, thanks for your talk. I was just curious. So the in the equivalence that you had on the previous slide, so this is between path categories and comprehension categories. Do you know what it looks like if you instead take split comprehension categories? Like, does that correspond to something in path categories, or?
So path categories are generally like non-split in the sense that we don't have nice choices for these things. And the idea of having this equivalence is that after this we could apply one of the ways of splitting a comprehension category. So we can start with a path category, turn it into a comprehension category, and then split that one to get an actual model. So you could also define such a notion of like a split path category by equipping it with choices for pullbacks for vibrations that respect all of the things you wanted to respect. Yeah.
Okay, we have time for more questions.
Maybe that's more clarification. I mean, if we have just weak beta for equality type, that do we know that is equivalent to have strict beta, or is it still open?
So that's, I think, still open. So weak bit, you mean propositional?
Yeah, propositional.
Yeah. So sort of comparing type theories with more definitional equality and less definitional equality, I think there's still quite a lot of open questions there. So we know it for the two extremes, yes. But then we get uniqueness of identity proofs.
UIP, without UIP, that's...
Yes, no, that's the big question. Yeah. I think Raphael Bocquet has some work on that, but I mean, even the question of this intentional type theory versus axiomatic type theory, I think is still open. So there's one candidate for why it's maybe not conservative, namely this notion of binder extensionality. So normally we have function extensionality, and that's equivalent to binder extensionality, where binder extensionality means if we have, so basically the same, that so function extensionality is a notion for lambda, which is a binder. If we generalize that to other binders, then we get binder extensionality. And in intensional type theory, we know these two to be equivalent. But the proof for that equivalence doesn't seem to work in axiomatic type theory. So that would be maybe, so if you can show that that statement of that equivalence is not provable in axiomatic type theory, then we would be able to show it's not conservative. But that is still open.
Okay, thank you.
Thank you for the talk. I was wondering whether there was a reason why you would prefer this notion of path categories, or how would it compare to tribes, and why you have this specific settings instead of just relaxing. So I imagine you could define this starting from tribes, or at least a different phrasing, and I was wondering whether there was a reason for that.
So there is a paper, let's see. So in this paper by Van den Berg, he compares it to these tribes, or other notions by Joyal. And I think sort of still the main point there is that if we equip these tribes with maybe propositional identity types, or identity types that only have the propositional beta rule, then we still have quite complicated notions. Because as you saw in the syntax of type theory, the elimination and the computation rules are really, they become quite hairy. We have this additional delta, we have this equality that we have to care about. So sort of this idea that we can capture everything by just saying that reflexivity is an equivalence is, I think, a nice way of modeling it. And we can compare it or prove equivalences with the normal notions, where we have all four of them. But specifically the connection with tribes is in this paper by Van den Berg.
Okay, let's thank Daniel again. We'll have time for more questions in the lunch break.